which part is most critical one, so in the worldwide competition with the Samsung, the Intel, is which part?
Okay. Billion-dollar question. Well, everybody is using the same wavelength. Okay, right now it's 193. If EUV becomes successful, it will be 13.5. It's more than order of magnitude shorter. Okay, but everybody will be using the same. Everybody will be using the same NA because it's under the control of your supplier, same NA. Now, even with all the optimized illumination and so forth, they give you a tool that you can really change your illumination randomly, anything you like. So that's something that we can do something. We have a lot of people who can do simulation and who can do all the manipulation and to optimize this. We call it source mask optimization. Okay, to customize your illumination to the specific pattern combination you have. Okay, that is difficult, but there's something we can contribute, and that's where you make a difference. Okay, between Intel and Samsung and us. And the other thing is also called mask illumination, mask optimization. How do you design a better mask pattern to come to more fidel image on the wafer? It's also where you test the lithographer's competence. Okay. Now, nowadays, resolution can be taken care of pretty well. If you cannot, you can always use boost force. What? In terms of boost force means I will do more pattern. I would, instead of triple, I'm going to do quadruple patterning. Okay, instead of 193, I go to 13.5 and whatever. Okay, change the wavelengths, change the energy. If I'm using E-beam, instead of 50 keV, I go to 100 keV and so forth. Change the resolution. Okay, but overlay is something that is very tough because overlay is mechanical. Now, is any one of you in mechanical engineering? Have you ever imagined you want to control that overlay to less than 1 nanometer over a 300 millimeter wafer? Remember, I taught you that little hair, okay, and how many cells you can fit into there, and you have to control it to less than 1 nanometer overlay over the whole wafer. It's tough. It's tough. And nowadays, if you ask the supplier to improve the overlay for you, between when we were at the 7 or 8 nanometer regime, when you drop 1 nanometer, is $10 million. $10 million per 1 nanometer. Okay, and pretty soon you're running out of room. Okay, we are already working at 4 or 3 nanometer region. It's going to be tough. The other thing that's going to be tough and that will differentiate us is defects. Defects. There are a lot of know-hows in the manufacturing environment to control the defects. Okay, and it's a very sensitive, critical parameter for yield. Okay, you have defects, you lose yield. Okay, and it's not simple. It's not something that we can go and use a complicated equation, high order, and this and that, and solve that great equation and get the problem solved. Okay, it's a lot of nitty-gritty details and a lot of debugging, detection, okay, and trying to catch something that's changing by itself. Okay.
Follow-up questions. So you need to actually, so your technical improvements is only depending on the machine from the supplier, right? So the room for the playing around is quite limited by the machine. Am I correct? So how is the cooperation or relation to the machine supplier?
The relation to the machine to the tool supplier is very important. Very important. I always told my supplier that they are actually my customers. They are not my supplier. You guys in the university don't know the difference between a supplier and a customer. It's a very high difference between customer and the supplier. Well, anyway, it's important, but it's only changing the playing ground. But everybody with enough money will be able to achieve that. Okay, so what we're following up is very important. For example, in our mass optimization and in our proximity correction, we got a team of more than 200 people to do that. Okay, and we need a lot of very good physicists or chemists and so forth to be able to simulate and model the system very precisely. Okay, it's not easy. I mean, the supplier cannot help you. You have to be able to, from your experimental results, get your modeling, get your model correctly, so they can predict it correctly. And you don't always just get it in one try. Okay, and also how do you handle the data? How do you control the computing time reasonably, and this and that? There's a lot of work. Okay. All right. So that's why there's a very high barrier for people to enter into very advanced nodes, and is very competitive. We work very hard so that we can be better than Intel and so forth.
Okay, could you go back to the last slide?
Last slide.
Last slide. Well, you didn't mention, but you actually show the e-beam directed right.
Yes.
And could you give us a perspective on that?
Yes. Well, from this slide, you can see that the e-beam directed right is very rosy because it can handle any kind of solution. Okay, it's only using electron, and the reason is very simple. A 100 kV beam has such kind of wavelength is even much shorter than EUV wavelength. Okay, now why is it not still not there? It takes a lot of time to develop an e-beam system. I think we were working on a very promising e-beam system. We all designed what it's going to look like, how many columns. We have a target to achieve 100 wafers per hour. 100 wafers per hour at a reasonable price. Okay. Now, in the good old days, we used to have a problem with e-beam because e-beam is too slow. Well, e-beam you can deflect it very fast, but it's only one beam, right? And when we're doing optical, we're talking about massive parallelism. We're talking about 10 to the 12 of parallelism and so forth. So it's very difficult to beat with e-beam. But now, time has advanced to the point that now we have MEMS, okay? And then we have supercomputers, which are actually our common user computer is much faster than the supercomputer of the good old days. We can handle a lot of data in terms of how many gigabits per second and so forth. That is achievable. So the time is right for e-beam lithography. Okay, we can design the right column. We can use also massive parallelism, and we can handle the data reasonably well and with reasonable cost. Okay, unfortunately, it got started later than EUV, and there's a lot of momentum in EUV. Okay, for example, in 157 nanometer days, people were trying to resist immersion lithography because they invest already $700 million in 157, so they want to keep it. Well, it didn't work out. Immersion went on. But for EUV lithography, people must have spent more than $2 billion on it. Okay, so there's a lot of inertia in there and a lot of investment that they have to protect. And the other thing is that for e-beam, you also need dedicated team and reasonable size team and so forth. And right now, I think that industry momentum is not there. We can do some feasibility demonstration, okay? But in order to get a real tool, industry robust tool, it takes a lot of manpower and a lot of investments and very good brains too, okay? So I think we're losing time. I think we're also losing time in EUV. Right? We're talking about 5 nanometer nodes, and at 5 nanometer node, we don't even need EUV. So you almost have to go to the application where you have to do double patterning on EUV. Okay, and EUV has its own bag of worms that I don't have time to go through. So you have to get through all those in time. Okay.
Any other question from students?
When you collaborate with, for example, like ASIAA, create the best photolithography machine, then how do you tell them don't sell hardware to the Intel, Samsung, IBM, then they can make the TSMC make big money? Yeah, how do you do this? Thank you.
Why did you ask me this one? Because you found that we did it? We were successful or what?
You already, for example, you already create the best photolithography machine, and then you can create a very nice chip, for example, below the 5 nanometer.
Mm-hmm.
So, but the ASIAA can sell this machine to your competitor, like Samsung or IBM or Intel. How do you talk to them? Don't do this.
There's no way to tell them not to do this. There's no way to, because they are my customers, they're not my supplier. Okay. Well, we have to compete on other things. For example, on the photoresist. Okay. We will have very good chemists and so forth, and polymer chemists and so forth. We can invent some very good, unique resist. Okay. And we also have very good process engineers who have to develop good processes with large process window and this and that. So the teamwork becomes very important. We not only have to confine our work with lithography, we also have to work with our etch engineers and chemical, mechanical polish engineers and so forth. So it's an integrated effort to get the entire process going on with high yield. Okay. That is very difficult to reproduce. Let me give an example. SMIC, right? We know SMIC, what is semiconductor manufacturing, whatever. That's the one in China that moved from Taiwan to China. Okay, they were trying very hard to catch up with us. It's not easy because the barrier is high. All those know-hows together is very high.
So what's down the road? I mean, we know then you're 10 nanometer, then 7 nanometer, I guess, right? 5. Okay, but it's not just lithography, right? There are a lot of material problem and this and heating problem and this and that. And people talk about some new material like a graphene topological insulator and something like this, and some spin polarized device and things like that. So what does TSMC see in the future? Do you have any plan that you can have a collaboration with the university to develop some new device, beyond this silicon based, or integrate with the silicon device and things like that?
Well, TSMC is very interested in any good idea to extend the life of devices and so forth. We are looking very hard ourselves at different new ways to move Moore's law. It may not be, well, personally, it may not be geometry, okay, because I'm talking about overlay and those things, okay. But there are a lot of rooms in there. For example, how do you do clever design? Okay, design that's less sensitive on overlay. Design that will give you a much better performance. For example, in one of our generations, we didn't reduce the geometry that much, but the design gave us increased the density for us. Very good design. Okay, so I think there's a lot of rooms in those areas, and not to mention new devices, new materials, and so forth. But we are always very eager to learn about any innovation the university has. Okay, and we're always very eager to work with you guys.
Any other questions? So, okay, I have the two questions. First, I think you, from what you just stated, that even the country like the mainland China, they have a lot of money. They really want to destroy Taiwan's same industry, for example. But for me, it's not just money. It's a lot of expertise and a lot of brand inside there. So in that way, I think TSMC is not afraid of the competition from mainland China.
Well, we have been competing with mainland China for many years. This is not new. Yeah, we've been competing with them for a long, long time. Well, we're competing with a lot of very tough competitors, right? Like Intel, like Samsung, and so forth. We have competed with quite many older competitors that we may have forgotten. Okay, yeah. So we'll see. What TSMC is good at is at innovation and commitment. Okay. Well, actually, we have two ICs. IC. The first IC, the first I is integrity. We think integrity is most important. It's the basic of everything. Okay. So we think we want to uphold integrity. We want to commitment. We want to uphold commitment, and then innovation. Without innovation, we cannot be ahead of other people. And the last is customer relationship. If you have even the best product in the world, okay, if you not can sell it to the customer, it's zero. And mind you, TSMC has a lot of customers. TSMC has more than 400 customers. We really have to pay attention to each of them and help them win. Okay, I mean, TSMC win doesn't mean anything to them. They want to win. Okay, so we will help all our 400 customers and make them feel happy and comfortable, and help them feel like they will come back again. Okay, so our ICSC, we think we have some winning cards in our hand. Also, we think our R&D is very high level. We've got strengths in R&D. We have strengths in manufacturing. Manufacturing know-how is also very important. Because even if you have something, you have to be able to scale it up. And you have to be able to scale it up consistently and economically. Okay. And then we have our marketing know-how.
Is that the last word? Since you are in physics here, how do you say words or encouragement to the young minds?
Okay, good. Well, so you young people, I look at you and I'm thinking about myself 50 years ago. Well, it's 1963 to now, it's more than 50, something, close to 50. Yeah, close to 50. Now, you guys are much more privileged than we. At that time, we said, well, don't quote me, okay? We said, I didn't say, we said, first class students, second class equipments, third class faculty. Okay, I think the situation is different. Now, you guys have a lot of privileges. You got much better faculties, you get much more laboratory equipments, okay, and you get much more competition, okay. You have to publish in well-established journals and this and that, right? And also you have much better tools. We were using what? 计算纸. You know what 计算纸is? Yeah. In campus, you see, one of the reasons the electrical engineer looked better than physics major was that we had a 计算纸, right? And when you're riding a bicycle, you have a 计算纸. Okay. But anyway, you don't need that. Okay. You have powerful computers, and you have all those nice tools to help you, and you have all the stimulations that help you. I always tell the newcomers to TSMC that, it's your responsibility to come to innovate and make Moore's law sustain. Okay, we do our part, but now you guys with new perspective, with new enrichment and and new thinking and so forth, you have to now make, even for Taiwan, okay? The Taiwan future is in your hand, especially you guys who are in Taida, okay? It's in your hands, okay?
Good. Thank you. Is that let's thank Dr. Bernie again.